Good afternoon, everybody. Thanks for joining today's NC-CAV seminar. We are delighted to have today's speaker, Dr. Hisham Rakha. Dr. Rakha is the Distinguished Professor of Engineering in the Department of Civil and Environmental Engineering and a courtesy professor in the Department of Electrical and Computer Engineering. And he is the director of the Center for Sustainable Mobility at Virginia Tech Transportation Institute. His research focuses on large-scale transportation system optimization, modeling, and assessment. He works on optimizing transportation systems operation, including vehicle routing, developing various network and traffic signal control algorithms, developing freeway control strategies to reduce their energy consumption while ensuring their safety. A key component of these control algorithms are the tools needed to predict the system evolution while capturing the stochasticity of these systems. In this area, Dr. Rakha and his team develop and apply modeling, artificial intelligence, and statistical techniques to predict the spatiotemporal evolution of the system. I'm not going to read the all details. Feel free to read the flyers of today and be aware of more research that Dr. Rakha is conducting. His great achievements you can observe already from the bio of Dr. Rakha, and he's also just another thing. He's also IEEE Flow as well. So I want to reserve time for the great talk that we have today, indeed. So with that, Dr. Rakha, the stage is yours, and thank you again for accepting the invitation for today's talk, and we are so excited about it. Thank you.
Thank you very much. It's a pleasure to present. Let me just share my slides here. There it is. Okay, I'll get into presentation mode. What I'm going to do before, maybe I'm just going to remove my video before, just so that bandwidth is not overloaded, I guess. Okay, so as I mentioned, it's a pleasure to talk to you. My presentation is going to be, I guess, focusing on these three aspects: optimization, modeling, and assessment. I would say this is large scale. So we're looking at citywide transportation systems. So basically, I guess you all are aware of that, and you have, I guess, a center focusing on this, but we're all aware that with, I guess, connectivity of vehicles, you have connectivity of our phones. So basically the traveler, the vehicle, the pedestrian, the infrastructure are all being connected to one another. So this allows us to share information that we could not easily share before. In addition, I guess we're all aware of the work in terms of automation, whether it's Google and other entities looking at trying to develop automated vehicles. So you have these connected automated vehicles that can communicate with one another and also have some form of automation. I guess right now we've got level 2. I believe Mercedes now has just released level 3 automation. I believe I saw that on LinkedIn. So basically we're looking at level 2, level 3 automation, and then the final outcome will be level kind of 5 automation. The other thing, I guess, that we're very aware of is global warming, climate change, that basically is posing a big threat to the world, and we're seeing a lot of outcomes of that in terms of wildfires in the West, these hurricanes that are hitting different places, and the changes in the weather, the extreme weather conditions, either extreme heat or extreme cold, and so forth. And so this presentation is going to try to tie these three things together, which is the connectivity, the automation, and how can we use the information that we receive through connectivity, the automation by controlling these entities, whether they're cars or intersections, to try and reduce the carbon footprint of the transportation system as a whole. So what I'm going to do is go through a number of projects that we worked on in this area. So the first one is a project that was funded by the U.S. Department of Energy, the ARPA-E program. This was led by the Palo Alto Research Center, PARC, and we were subs to them. And these are some of the publications that came as a result of this project. And so basically, the project entailed some application, which is to the right here, where PARC had developed this GoLA app. This GoLA app is different than what you have in Google, in the sense that if you want to go from point A to point B in Google, you will tell it either I want to drive, or you want to walk, or you want to take public transportation. Once you give that information, then Google will estimate the optimum route, and they've also developed some eco-routing algorithms. I believe they're working with NREL to come up with those fuel economic routings. But then it will compute the optimum route to get from point A to point B. So let's say if you're driving, it will tell you, take these set of links to get from point A to point B. And that gets updated as you travel along the trip. So if an accident happens, we were using Google, both serve as probes. So that's observability of the transportation system. And we also serve as tools for Google to manipulate, which is the controllability. If we follow the recommendations that Google makes, then we are actually the tools that Google is using to manipulate the conditions on the transportation system. Now, what PARC did was a step further than what Google did or is doing. What they would do is, you want to go from point A to point B, and they will tell you, for example, you could drive your car to this subway station. You could ride the subway to this subway station, get off, take an Uber from this point to a bike share station, pick up a bike, ride the bike for this portion of the trip, drop it off at this station, and then walk for the remainder of your trip. So basically, it's a multimodal trip. And the beauty of this app was that you would pay once, and a portion of that payment would go to the subway system, a portion would go to Uber, and a portion would go, for example, to the bike share system. And this would all be happening behind the scenes for you. And the question we were trying to answer was, if we could control 10% of the travelers in an urban area that had more than 3 million trips per day, what would be the potential fuel/energy savings that we could achieve as a result of trying to make recommendations to these travelers that are fuel efficient/energy efficient. Now, given that the app was for the Los Angeles area, we modeled the Los Angeles network, which is the one shown just to the left of that button there. Let me see if I can change my thing here to a laser pointer here. So this is the network of Los Angeles, the greater Los Angeles area. The thing that we also worked on was that if we were providing the information to these travelers, we want to try and provide recommendations that would be highly acceptable by that specific traveler. So, for example, I know that Hisham is not a very athletic person, would not be interested in riding a bike. So I would not give a recommendation to Hisham that involves using a bike share, for example. And so we used some artificial intelligence techniques to try and infer and learn from the characteristics of that traveler what would be good recommendations for that specific traveler in order to be more successful in having that traveler follow our recommendation. And this was a 2.5-year project. And that 2.5-year project can be summarized in this one sentence here. And this one sentence said that if we were to provide information to 10% of the travelers in Los Angeles, in the greater Los Angeles area, so you have more than 3 million travelers, approximately 55% of the 10% would accept our recommendation. And those 55% would result in a 5.5% of the total population, given it's 55% of 10%. And those would produce a 4% reduction in energy as a result of following our recommendation, and a 20% reduction in delay. So that's a summary of what we came up with. And my next couple of slides will be, how do we come up with that conclusion? So in order to do that, of course, we could not test this app in the real world. So we had to test it in a hypothetical world, which is a simulation environment, a microscopic simulation environment. And our argument was that whatever simulation tool that we use to evaluate this tool, it has to be of higher fidelity than the tool that is used to come up with the recommendations. If we use the same tool that we're coming up with the recommendations to evaluate those recommendations, we would be biasing our conclusions, because basically reality would be consistent with what we are perceiving reality to be. But in reality, what we use to compute our optimum routes is going to be off from reality. Is that correct? So, and that's why we elected to go with a microscopic simulation of the network in order to evaluate the benefits. I should mention that there were 5 teams that were doing similar work. One team was MIT. One team was led by the University of Maryland. One team was led by Georgia Tech, and one team was led by NREL. And so each of those teams had a different urban area. So, for example, Georgia Tech, of course, would have Atlanta. University of Maryland, they had the greater Baltimore, Washington, D.C. area kind of as their modeling framework. And so each entity had a different urban area that they tried to quantify their system. And of course, each team had a different system. In our case, it was the park application that we were looking at. So in order to make this feasible in terms of a modeling exercise, given that we have to model over 3 million travelers and track these 3 million travelers at a decisecond level, we used a hybrid modeling approach where we had the integration software, which is what we develop in-house here, which models microscopically every decisecond the movement of vehicles. But in order to have this scalable, we only modeled microscopically on the freeways and the major arterials, because our hypothesis was that most of the traffic congestion occurs on the freeways and the arterials, and the local streets typically are not congested. So we can get away with using a mesoscopic approach to simulate the local streets, given that they're less congested. We also had to develop a tool to model the railway system, because we are modeling also people taking the subway system and the railroad system in the greater Los Angeles area. We developed a tool, the BB-Sim, which modeled the pedestrians and the bicyclists. And we had this simulation coordinator that would move that person. So if that person now likes to drive their car from their origin, so they will be on the local street, so they'll be modeled mesoscopically until they hit an arterial, so they get to be modeled microscopically, so they get into the integration software. And let's say that they park at a metro station parking stop, so they would then get onto the railway system, and then we would track them. So that's how we were tracking these individuals through this simulation coordinator that would track the individual person as opposed to the vehicles or the trains and so forth. When we wanted to compute the carbon footprint of a specific traveler, we would have to divide by the number of passengers that are with that person in the car. Or if you're taking the train, let's say there are 100 people on the train, then you contribute to 1/100th of the carbon footprint of that train at that instant in time over that delta T. So that's, let's say that's every decisecond. So we track that train every decisecond, and we track how many people are on that train. If some people get off at a station, then that will your contribution would change depending on the ridership of that train at that instant in time. And so that's how we did it. And as I mentioned, we elected to model the major roadways microscopically and the local streets mesoscopically because they were less congested. So in total, we had 170,000 roadway segments or links that were modeled mesoscopically and 10,754 that were modeled microscopically. And this just shows you the greater Los Angeles area. This is actually downtown Los Angeles to the right here. The blue areas are the roadway segments that we modeled microscopically, and the red segments are the roadways that we modeled mesoscopically, which so they would be the local streets driving from each subdivision onto to get you all the way onto the arterials and the freeways and so forth. We also divided the network in order to get, our objective was to try to get this to run at the speed of real time. And so in order to do so, we also segmented the network into 5 sub-networks. Each of those, so these are now the microscopic ones. So it's the blue roadway segments that now we're taking them and dividing them into sub-networks where we would model each sub-network on a different machine, and then we would synchronize those sub-networks. Now, what we miss by dividing this full network into sub-networks is that any congestion that spills back from on a roadway segment in sub-network 3 onto sub-network 4, we will not be able to capture that spill back onto sub-network 4. So you try to make those breaks at locations where there's not spillback in terms of congestion, but at the same time, you want those networks to be similar in size so that they run at similar speeds, so that basically you're not waiting for one sub-network to be finished while the other ones are all finished. And so that's basically how we did it. And we were successful in getting this to run in real time. This just describes the model that we developed for modeling the trains. So this was a model that we developed in 2018 to model the train systems. And these were electric trains that were in Los Angeles. One thing to mention in the modeling of the trains is that the power that you consume from the battery is equal to the power on the wheels, or in this case, the tracks of the trains, divided by some efficiency. So you have your driveline efficiency, your electrical motor efficiency, and your braking efficiency, plus the power that you have to exert to run your AC system, for example, any auxiliary power that you have to run. Now, if you're running an electric system, the energy can be flowing from the battery to the wheels, which is in this case here, or it could be flowing in the opposite direction from the wheels charging the battery. And in this case, this is the example here, when the power on the wheels is negative, it's actually charging that battery. And so basically you add in another efficiency, which is the brake regeneration efficiency, which is some exponential function that we found that decays. So the more aggressive you decelerate, the higher the efficiency of your regeneration in your system is. And then from that, we can compute the energy that we consume every delta t. So basically, based on the power, you multiply the power by the delta t that you're computing that over. So in our case, it's every decisecond. If we multiply it by every decisecond or every second, we get the energy we consume over that second. We sum it up across all the seconds in our trip. That gives us the total energy that we consumed in our trip. We sum it up across all the vehicles. That gives us the total energy we consumed in the entire network. If we're trying to compute the energy related to a specific individual, then we divide this energy by the number of passengers on that train or that vehicle, and that gives us the contribution of that person to that energy that is consumed. In addition, we developed models that would model the bicyclists. So it takes into account both the bicycle and the person riding the bicycle. So I could be riding a top-notch bicycle, but I'm not a very good bicyclist, whereas Lance Armstrong could be riding the same bicycle and he would be able to ride at a much faster speed than me. And so you take into account who the person is riding the bicycle, because they're providing the power, and the bicycle, given that there are certain characteristics of the bicycle. It might be a light bicycle, it might be certain characteristics, and so we take those into account when we model these bicyclists. I should mention that we wanted to also come up with the possible upper bound of this system, and I'll show this here in this next slide. So the upper bound of the possible benefits, remember, we're trying to control the travel of 10% of the population. So what we said is, let's say that 10% of the population just decided to stay home, just similar to what I guess COVID did to most of us, I guess, during the peak of COVID, where most of us were working from home. And so basically that would be reducing the traffic demand from 100% to 90% of the demand. And that would be the upper bound of the possible savings, given that if the best scenario would be that you just work from home, so you don't consume any energy to travel to your work. And that actually provided a 30% reduction, somewhere between a 30 and 37% reduction in delay, and somewhere between a 9 and 10% reduction. Sorry, the mean was 9%. It was between 10 and 8 point something, and 37 and 24. So a mean would be 9% and 30%. And this is for the AM peak, which is 6 hours. I believe it was from 6 in the morning until noon. And then the PM peak was from 3 p.m. until 9 p.m. So it was 6 hours as well. Similar results we got for the PM peak, which is a 9.3%, an average of 9.3% reduction in energy, and a close to 29% reduction in vehicle delays. And this just summarizes the conclusions that we came up from this study. We also looked at eco-routing of vehicles, that if we were to route them in energy efficient ways, we found that we could save, if we compared the energy of the vehicles that were eco-routed versus the ones that were not eco-routed, there was around a 70% reduction in their energy consumption. For eco-driving, given that the greater Los Angeles network is extremely congested, we were unable to achieve benefits in the eco-driving because you were constrained more by the traffic around you, and you had less freedom to drive in a more energy efficient manner. So this will conclude the first batch of my, the first project. So maybe, would you like me to open the floor to any questions, Ali, or should I just continue if anyone has any questions on the first project?
Maybe if there is a quick question, whatever we can have right now, and then later more questions.
Sure. So if anyone has any questions, if not, I'll just continue. Okay, so it seems there are no questions, so I'll just continue into the next one. So the next one is actually, I guess, close to, I'm assuming close to your area of expertise, because it's about the integrated modeling of the transportation and communication systems. So I guess typically you have these two approaches to modeling this interaction. You've got the transportation engineers like myself, who in the previous study that I presented, we completely ignored the communication system, assumed that there was infinite capacity, packets were not delayed, all packets were received, and everything worked perfectly. So that's one extreme. You've got the transportation engineers doing that. At the other extreme, you have the electrical engineers who model the communication system at some very high level of fidelity. For example, using NS3 or Omnet or UpNet or whatever tool they're using, but ignoring the, I get nitty-gritty movements of these vehicles that are communicating with one another. Now, there have been attempts to try and combine these. So, for example, work has been done to develop VEANS, which is, I believe, UpNet++ with Sumo. They integrated them together. So we started that same kind of approach in 2015, which was we developed VNet Sim, which is our integration software with Omnet++. However, we quickly realized that this is not scalable. And the bottleneck is typically on the side of the communication modeling, where if you're tracking in these packets at these microsecond levels with these different channels and sub-channels and all these different level, these very high level of fidelity, it's computationally extremely extensive. And if we wanted to model this Los Angeles network, it would be impossible to do so. And so we elected to come up with what seemed at that time or the impossible, which was trying to come up with some integrated modeling framework that models the communication system and models the transportation system, but can model it at large scale. So this is what we ended up in with the work that we did with Ford. This is in 2021, so last year, where we developed this large-scale modeling framework. In this case here, it's direct cellular vehicle-to-vehicle, so direct CV2X, release 14, which is the 4G LTE. But previous to that, we also looked at using VANET networks, where we used DSRC, and one of my students, Ahmed Elbiri, he developed an analytical model for the DSRC communication system, and we integrated that with our traffic modeling system. And I'm going to go into the specifics of this in the next couple of slides. So the motivation that this came up from was in working with some of the communication folks when they were trying to model this. So typically, they would model this in a non-integrated form. So basically, you would run the traffic simulation software, generate the trajectories of these vehicles, and then use those trajectories of those vehicles as the traffic mobility, and then run on top of that, those trajectories, the communication system. And what they found was if they modeled 2,000 vehicles for a duration of about 20 to 50 seconds, it took them days to model that, to model the communication system on top of these trajectories of these 2,000 vehicles. And again, this is also not integrated. So what I mean by integrated is that the application that I'm running, this connected application, let's say it's a dynamic routing system, depends on the communication system in providing the information that I need for my application. At the same time, if my application is not working very well and it causes traffic congestion, vehicular traffic congestion, then that will cause more congestion on the communication system, which would then affect the application, which would then affect the communication system. So basically, you get into this vicious circle where if the communication system is losing packets and delaying packets, then that affects the application. That in turn increases the traffic congestion, which in turn affects the application, and you just get into this loop that actually pulls the whole system down. And so we developed this integrated framework where we tested it on just subnetwork number 3. So this is this one here. This one here, the downtown Los Angeles. So we tested it on this area here. And this is 145,000 vehicles in 1 hour, with approximately 30,000 vehicles concurrently on the network at the same time. And we were able to run 1.86 hours of real time, of simulated time, in 1.5 hours of simulated time. So we're running it faster than real time. The coupling of these two systems, the communication system and the transportation system, is done somewhere between every 1 second and 30 seconds. The more congested the network is, the less frequently we do the coupling in order to speed up the computation. So we're losing some accuracy and fidelity of the system in order to get scalability of the system. Basically, we are abstracting the communication system at 1,000 hertz and the traffic simulation at 10 hertz. We used an analytical model that was developed by some Spanish researchers, the lead author Gonzalez, in a paper, I believe it was in 2019, if my memory is correct, but I'd need to go back and check. But basically, we used their model and we had to modify it to be able to model, because when they developed their model, typical of communication experts is that they model it on just a linear system, so just one roadway that is linear. In our case, we're modeling it on a network where you have a two-dimensional roadways. So you have some roadways perpendicular to this roadway and parallel to this roadway and along this roadway. So we have to take into account all the vehicles surrounding this specific vehicle in order to identify the possible pairs of vehicles that can communicate with one another. So V2V vehicles, we came up with ways that we could speed up. So one of my researchers, his name is Muhammad Farag, he came up with ways that we could identify. We divide the network into a grid, and we know which vehicles are in which grid, so we can identify which vehicles can communicate with one another very quickly without having to search all the vehicles in the network, so in order to speed up the computations and so forth. So we had to do lots of tricks in order to get this to work at the scalable level that we wanted it to run at. And this just shows you an example of the downtown Los Angeles network. So this is the gray area of the roadways, and superimposed on that, I have a table that's provides the packet delivery ratio for that specific cell. So 0.73 means 73% of the packets are being delivered and 27% of the packets are actually being lost. And so now we're working on taking this the next step, running applications. And so we have to generate, for example, random numbers. And if that random number is less than 0.73, then that packet is going to be delivered. If it's between 0.73 and 1, then that packet is going to be lost. And then we just, that application is going to have to deal with now older data, and then how that application, we'll see how that application degrades as a result of this loss of information in the system. One other piece of work that one of my PhD student, Ahmed Al-Birri, did, which we were looking at DSRC. The neat thing that we found in this study was that if you were to do it the way the transportation engineers typically do it, which is ignore the communication system, the benefits of our dynamic eco-routing system typically increase or flatten out as the level of market penetration of these connected vehicles increases. Now, at low levels of market penetration, I have low observability and low controllability. At high levels of market penetration, I have very high observability and very high controllability. And so under those conditions, I should get better benefits than for the low levels of market penetration. But if you consider now the communication system, when you go into the high levels of market penetration, you can overload the communication system. And what we found was that the sweet spot was around 20 to 30% level of market penetration, where we would get the highest benefits. If we went higher in the level of market penetration of these connected vehicles, we would typically degrade the communication system, which would degrade the application. And if we went lower than the 20%, we would have very low observability of the traffic conditions and controllability of these vehicles, that we couldn't do much benefits in the system. So that's the second project, and I'll open the floor to any quick questions that you might have on project number 2.
Maybe a quick question, moving beyond DSRC and then perhaps moving toward 5G, what's just kind of guesstimate how that trade-off point would be increased, or any comment on that?
Yes, so actually it's interesting you're asking that question, because that's a current project that we're working on. But I'm not a very good expert in 5G, but my understanding is with the 5G, you go to the cloud. So the reliability of receiving the packets is much higher. However, you would have some delay as a result of communicating to the cloud and then the cloud communicating back to the vehicle. And so it's more kind of delay of packets as opposed to loss of packets. But we're still looking into the literature right now of trying to find an analytical model that is out there that we can use. So basically, we'll just be replacing the subroutine that we have for the 4G LTE with a 5G communication modeling framework, and then we would be testing these applications. I should mention that I do have another project with another entity. I don't want to disclose them, but they went another route where they provided, so they ran their very detailed communication tools similar to NS3, for example, and generated for us packet delivery ratio curves as a function. So on the x-axis is the distance between the two vehicles that are communicating with one another. So at 500 meters, typically the communication is, the PDR is 0. And then when you're on top of, very close to one another, PDR is close to 1. And you have some inverted S-shaped curve that goes down. But those different, you're going to have different curves for different traffic densities. and also different sets of curves when you have a line of sight versus when you do not have a line of sight. So they provided us with the curves for the 4G LTE that we basically used instead of the analytical model. And the other approach that we could do is then have them generate those same curves for 5G and then model that the 5G communication system within the context of this specific application that we're trying to model. I hope that answers your question. In a nutshell, I really don't know the answer because we're still trying to figure out the answer of that. But at the extreme, if we were to assume that the 5G is perfect in the sense that all packets are received and no packets are delayed, then that brings us to what the traffic engineers assume. Is that correct? That when they ignore the communication system, their assumption is the communication system has infinite capacity and infinite delivery, that basically no packets are delayed or lost. So that will give you the upper bound of the potential benefits of that system. Any other questions? Okay, so let me go into the next application, which is a project that we had for the Department of Energy that we just completed. But basically, it's a bi-level controller. At the upper level, we have a router that is trying to route vehicles in an energy efficient manner. And we have a strategic speed controller that is trying to regulate the flow of traffic entering a congested region. So let's say in downtown Greensboro, you have some traffic congestion. So what you could do is try and reduce the amount of traffic entering into downtown Greensboro in order to disperse the congestion in downtown. And in trying to regulate the flow of traffic entering into downtown Greensboro, there are two approaches you could do. One of them is I could use traffic signals and reduce the amount of green time that is being allocated to the traffic entering into this region. Alternatively, I could be controlling the speed of the traffic. By controlling the speed of the traffic using the fundamental diagram, we're actually reducing the flow of traffic entering into this congested region. So we can be controlling the flow entering by controlling the speed of these connected automated vehicles. And that's what we're doing at the upper strategic controller. At the lower level controller, we're actually controlling the dynamics of this vehicle. On the one hand, to the left here, this is when you're close to signalized intersections. So we assume that you can receive signal phasing and timing data from the traffic signal controllers, which is SPAT information. And using that SPAT information, we optimize the trajectories of these vehicles in order to minimize their energy/fuel consumption. To the right here, on the freeways, we try to move the vehicles using, I guess, an eco-CAC system that platoons vehicles and has these platoons drive in ways that would minimize their energy consumption. So basically, if there's a terrain that is you've got a downhill followed by an uphill, what I could do is drive a bit faster on the downhill in order to get some momentum, so that when I go on the uphill, I need to press on my gas pedal less because I exceeded the speed limit coming down the downhill, that I can use that momentum to go on the uphill section of roadway. So that's, in a nutshell, what we're trying to do. And as part of this work, we developed this vehicle-specific eco-routing model that basically uses information on the cloud. So basically, when a vehicle traverses a segment of roadway, it sends eight variables about this segment of roadway that it experienced to the cloud. On the cloud, we fuse that information with other information we received from other vehicles. And then we send that fused information back to that vehicle for it to build its minimum path from that point onwards to its destination that is specific to that powertrain. So I use those 8 variables to build my minimum path. So if I'm driving an electric car, my minimum path, the optimum speed for an electric vehicle is around 27 kilometers per hour. So maybe 15 miles per hour would be what you would be for an electric vehicle. Whereas if you're driving a gasoline vehicle, it is more efficient at around 55 miles an hour. Conversely, remember when we talked about electric vehicles and trains, when you have stop and go conditions, you can regenerate your battery. And so electric vehicles actually thrive on congestion because that's better for the regeneration of their battery. And so you have this very conflicting objective where if your objective is to minimize energy consumption of an electric vehicle, you will be increasing your travel time very significantly. Conversely, if I try to minimize the travel time of my electric vehicle, I'm going to be increasing the energy consumption of my electric vehicle significantly. So we tried to implement this, and we developed this tool that can do this. We also looked at, I guess, what we call multi-objective routing, but here we show you here that that if you were to do a feedback routing, so an eco routing, that you are going to be reducing your energy, but at the expense of your travel time. So you can see here with a non-congested, I've actually doubled my travel time compared to if I were to route my vehicle to minimize my travel time. Here in the congested region, when the network is fully congested, I've actually maybe tripled my travel time. So if I'm trying to minimize my energy, it came at the expense of increasing my travel time by a factor of 300%. And so we came up with these multi-objective kind of approaches to route vehicles on the network. I see now that I've got about 8 minutes remaining in my presentation. So maybe I'll explain this one here, and then maybe I'll stop and open the floor to questions for this point onwards. Does it sound like a good idea, Ali?
Yes, I think that's a good idea.
Okay, so this was a project that we did. So this is now the strategic speed control, where I don't know if you guys are familiar with Northern Virginia, but this is I-66 going from Northern Virginia towards Washington, D.C. So Washington, D.C. would be to the east here. And this is the Dulles toll road that meets I-66. Basically what you have is it's a 4-lane highway, I-66, where you have the Dulles toll road meets it, then it goes to 3 lanes, and then at this point here it goes to 2 lanes. So it goes from 4 lanes all the way to 2 lanes. And what typically happens is every day around 3 p.m. you get congestion that builds up upstream of this 2-lane section that spills back all the way past this entrance of the Dulles toll road. So it spills back onto the Dulles toll road and continuing on to I-66. And so what we wanted to do is to develop the speed harmonization algorithm where we could control the speeds of traffic approaching this bottleneck in order to either prevent this bottleneck from breaking down or delay this bottleneck from breaking down. And that's what we could do. We could never prevent it because you've got so much traffic arriving. And so there's so much you can do when the demand is very high. But what you can do is delay the onset of congestion. We did this both in a simulation environment and we did it with real cars. So we had these cars, we had 3 cars driving side by side on the 3-lane approach to this section. And we tried to drive them side by side to create a wall that would prevent these other vehicles from overtaking these vehicles. We collected traffic data, we sent it to the cloud, we computed the optimum speeds of those vehicles, we sent it back to the vehicles, and we controlled these connected automated vehicles on this highway. And this was with LIDAS and the Virginia Department of Transportation. They actually were with us. They were actually in the car. We had some police officers in the car to make sure that everything was running smoothly. And then we also ran it in our microscopic traffic simulation software. And what we found was that if the level of market penetration was less than 10%, or we had less than 167 connected automated vehicles per hour per lane, then what the system did was actually made things worse. After we exceeded this 167 vehicles per hour per lane, or this 10%, we then started getting positive benefits of the system. And the reason we made things worse is these aggressive drivers see these vehicles slowing down too early, and they think that if I speed up and overtake these vehicles, I'm going to get to my destination quicker. But in reality, what we're doing is we're slowing you down upstream in order to relieve traffic congestion downstream so that you can reach your destination earlier. But it's counterintuitive to a driver. So I'm going to stop here and maybe open the floor to any questions that you might have. I had, of course, more stuff to present, but I think I'll just stop here.
Thank you so much for the great talk. It was very interesting, and all the 3-4 topics that you did cover today. So any question?
Hello.
Yes.
Yeah, I'm Benjamin, and thank you very much for the nice presentation. So I have one question on slide 5.
Slide 5, okay. Yes.
So if I understood you very well, you are modeling different parts of the route using the different simulation tools.
That's correct.
Okay. So I'm wondering how you are integrating the different simulation tools
So
to achieve your...
Yeah, so we developed these different simulation tools. So we could do it directly. So for example, the mesoscopic software was in Python, the RailSim was in Python, and the BBC was in Python. Integration is in Fortran, but we can make these into dynamic libraries so we can share information between these different simulation tools. So although they're different simulation tools, we're the same developers, so we could flow the information between them. And the flow of information was through this simulation coordinator, because the simulation coordinator is tracking the person. So Benjamin is first driving a car. So Benjamin is either in the mesoscopic or the microscopic simulation software that's tracking his car. Once Benjamin parks his car and gets onto the subway system, then Benjamin now is on the is in the train. So I have to track Benjamin now in the train. When Benjamin gets off the train, let's say he takes a bicycle, then I'm tracking Benjamin on the bicycle. And so this simulation coordinator is tracking Benjamin across these different modes of transportation.
Okay.
I hope that answers your question.
Yeah, it does. Thank you.
You're welcome.
Was it implemented in a sort of object-oriented or no kind of sequential tracking that you were doing among these simulations?
So the integration is not object-oriented. So the microscopic one is Fortran, given that Fortran is very efficient in dealing with matrices. So this one is not object-oriented. The other ones are object-oriented. The simulation coordinator is object-oriented. So So it's a mix and match, I guess, to answer your question.
Okay, thank you.
You're welcome.
Hi, can I ask a question?
Yes.
Yeah, so this is Dr. Lin from NC State. First of all, thank you for very innovative talk. And I have questions about the eco-routing application you present.
Yes.
The one with DSRC. So the finding actually quite interesting. In slide 18.
Yes, I think it's this one here. Yes.
Yeah. So yeah, my question is like, because you find out if there is a high market penetration ratios, actually it degrades the performance, and it's just about the energy efficiency, or in general it's not good to have that high penetration rate.
So for this, which was DSRC, where we were communicating to roadside units, we actually caused gridlock when we reached 75% of the level of market penetration, because the information was so old that we were providing these travelers that we actually made things really bad. So to answer your question, it was everything. It was energy, and we caused gridlock.
So your roadside unit will collect the information. Will it process, or it just push back all the information it received to all the users?
So first it sends it to the cloud. So we assume that the communication from the roadside unit to the cloud is fiber kind of so there's no delay in that system. Then at the cloud, you fuse the information. So similar to what I'm assuming Google does is, for example, when you're using Google Maps, you serve as a probe, you send your information gets sent to Google and it's tracking you. It fuses that information with other information it's getting from other travelers in the network, and then it sends that information back to the travelers, that fused information. Is that clear?
Yeah, so then what's the reason if there is extra energy consumption or delay? I know the delay is because you need to transmit the data, as you mentioned, from the roadside unit back to cloud and maybe backwards. And how about the energy part? Will it...
So maybe you're misunderstanding the energy. The energy is associated with the vehicles traveling, not the energy of the communication system. The energy is the reason the energy consumption of these vehicles is increasing is because they're stuck in traffic. They're just burning fuel. There's congestion, and so they're burning more fuel.
Okay.
Maybe on the same slide and same conversation, you are referring to bullet 1, to acceptable performance. Here, what performance you are referring to, and what is acceptable?
Where is that?
I mean, first bullet
says acceptable.
Yes, acceptable performance. How do you? What is the performance here? Are you referring?
So acceptable meaning that we're getting benefits of the system. So we're doing better. So at the let's say extreme condition, 0% level of market penetration means I have no observability of what's happening in the network. Is that correct? So if no one is using Google Maps, then Google cannot tell you what's happening on the roadway network. Is that correct? If 1% of the drivers are using Google Maps, then those 1% is a sample, a very small sample that's collecting information. If it's a very unbiased sample and a good sample, then it could be giving me good information, but most likely those 1% might be just traveling on, for example, the freeways, and I'm not getting information on the arterials or whatever. And so as the level of market penetration increases, I have more observability of the traffic conditions, so I can give you better recommendations because I have better eyes to see what's happening on the roadway network. But up to a certain point, that point is, if I exceed that point, then I start overloading the communication system. And so although those vehicles are communicating their information, a lot of these packets now are starting to get lost and get delayed, that information is getting old. And so then I get back to low observability again, although I have lots of probe vehicles providing information. Is that clear?
Yep.
And that's purely based on the DSRC, not
Yes.
like this. Okay.
Yes, so we're working now on the direct CV2X, and we're not observing that right now in the direct CV2X, to be honest with you. So these are still new results that we're working on. So it depends, of course, on your communication technology as well.
Yeah, definitely.
Yes. Yeah. And also I should mention that we assumed that our roadside units would be at the traffic signals. So we did a min-max, it was a min-max problem. We're trying to maximize the coverage of the network while minimizing the number of roadside units that we need to provide that coverage.
Mhm.
Subject to that, those roadside units can only be at traffic signals where power is available to power those roadside units. So we also had holes in the network where we couldn't capture the information there because we didn't have any traffic signals where the roadside units would cover that area.
Yep. Pretty interesting because actually, like my team is more focused on the cellular communication part, and to be honest with you, like as you mentioned, the C2V2X, they also try to address this latency and like package congestion issues that will reflect to the transportation side. Yeah, so I believe you are totally correct. Like the DSRC, if you just based on DSRC, especially the roadside unit or the signal point is not like dense, the benefit from communications might be an issue there. So that's why
Yes.
our solution is more like if there are multiple access points on the roads, maybe you can benefit from like network densifications to address these last mile issues. Yeah.
That's correct. And that's what we're working on right now, is looking at the direct CV2X and seeing how that, and we're actually doing the same application, the routing one, working on that kind of issue. But you're correct, yes. We're finding it less of an issue for the direct CV2X.
Thank you.
You're welcome. And so one of the things that we learned from this exercise is that it's very, you have to be very precise when you present your results, because you could make claims, but those claims are because of the assumptions you made in your coming up with those claims. So if, for example, when we used to do our runs, we used to assume that the communication system was not an issue and everything was good, and the more the market penetration was, the better the system performed. And then when you do DSRC, then you observe this other system, and then now when you look direct CV2X, you get these different results as well. So you have to be very careful when you present your results.
So any other question? One more question I do have. In project one, is it the recommendations that are being provided to the users? Is it going to be single recommendations, or you're going to be ending up with multiple recommendations based on, hey, for example, based on the time, based on energy, based on different factors that you are including, you are providing different recommendations to the users?
It's different recommendations depending, of course, on the traffic conditions and so forth. I mean, the user is singular in the sense that if it's Ali or if it's Hisham, I know their age is this, they're athletic or they're not athletic. They are so we try to use the traits of that traveler to I guess come up with recommendations that we felt would be I guess have a higher probability of you accepting that recommendation. Although, as I mentioned, only 55% of the people accepted our recommendation. So we were not very efficient at it, but we tried to model that from the traits of these travelers using some AI techniques.
You were those parameters, let's say the preferences of users, were given to your simulation, or you were learning over time?
No, they were given. So we learned offline from a sample of travelers in Los Angeles, and then we randomly selected from that sample the population, created the population, and then we were sampling from that population.
Thank you.
You're welcome.
Any other question? Okay. If not, thank you so much again, Dr. Raha, and